Hi, welcome back to some Quantlab programming sessions. Today we're going to do some portfolio optimization using some built-in functions in Quantlab. And we're going to do a classic mean variance optimization with linear constraints. And our constraints are going to be a minimum return on the portfolio, and also that we have a lower bound and upper bound that we can enforce. So you can find the help here in the function browser, and I have prepared a little workspace with some code. So let's go through this fairly quick. We take in a vector of instrument names. So we have some stocks, some Swedish banking stocks. Lower bound, upper bound, these are input arguments. Then we present some out arguments. We present the historical returns, and we present the historical vol in annual terms. And we also have the current quote. And we can also decide on the end date and how many days of the history we want to use in our optimization. So we have current date, 254 business days, mid-market quotes, and bounded or not bounded optimization. As you can see, it's blinking and moving around because the last day, this means that these quotes are actually in real time. So we're getting these quotes directly from the market. Here we have Millstream as the feed provider from NASDAQ. Okay, so what does the code do? Well, first we need to extract the historical prices. So we do that with a series. This is very similar to a data frame in Python. We can get all the series at once by looping the instrument, looping a vector of instrument, and then extracting the whole range of prices. And the rel change function works on the whole set, which calculates our daily returns, and we remove any daily returns that are not one-day returns by enforcing this with the calendar Sweden. So we're not getting any 2-day returns or 3-day returns that are clotting our covariance calculation. Then we present the historical vol, historical return, and the current quote to the table, as we said. And then we calculate the covariance. And as the last step, we actually pass these data to our minimum risk Markovich optimization. So we send the covariance, the returns, and minimum portfolio return, and the lower bound, upper bound if we're bounded. Otherwise, we remove those. So there are two versions of this. So then we can see what we're getting. So we have the stocks, and then we get the weights. And it's as simple as that. As you can see, the historical vol is fairly well correlated, reversely correlated with not having any weight, since we're simply optimizing so that we minimize the risk of the portfolio. If we do with bounds, then you can see that this stock that had more than 30% weight will then end up in its bound, and then the excess weight is distributed amongst the others in this optimization. So how is this optimization done? Well, it's a solver, a nonlinear solver, a quadratic solver to be more precise, implemented along the lines of Goldfarb-Ajani. And it, as we said, takes linear constraints, both equality constraints and non-equality constraints. And so here we can see how we have called the general function, the quadratic programming solver, in its most mathematical form. And we can see that we're solving for the unit circle this problem, and you can see that that's exactly what you get. Also a unit circle with unit values. Yes, that's what I wanted to show you, how to do some simple classic Markovich portfolio optimization with linear constraints, bounded and non-bounded optimization. Thank you very much.